Hello and welcome to the Hospital Near Me Medical Career Training Channel. Today we are working on the Medical College Admissions Test, or MCAT, to get you into medical school. Today's featured hospital is Glens Falls Hospital. Their address is 100 Park Street, Glens Falls, NY 12801. Their phone number is 518-926-100. Explore the fascinating world of physics with this educational video. We'll delve into concepts like upward vertical velocity, angular velocity, pendulum dynamics, work and energy, fluid dynamics, chemical reactions, and more. Discover how these principles shape our understanding of the physical world around us. Welcome to our physics deep dive. Today, we'll unravel complex concepts from upward vertical velocity to chemical kinetics. Whether you're a student or a curious mind, join us on this journey through the fundamental principles of motion, energy, and reactions. Do you need to talk to someone? Get confidential help through talking with a full-services professional listening company. Reduce your stress and increase your peace. Get problem-solving help today. Click on the link in the description that says, "Let me help you in life." Increase your peace. Get problem-solving help today. Question 1. Upward vertical velocity. Understanding motion. Upward vertical velocity. In physics, upward vertical velocity refers to the rate of change of an object's vertical position with respect to time when it is moving in the upward direction. This concept is particularly relevant in the study of motion, mechanics, and kinematics. Definition. Upward vertical velocity, denoted as Vy, represents the component of velocity in the vertical direction when an object is moving upward. It is measured in meters per second, MSECs, or any other appropriate unit of velocity. Acceleration due to gravity. When considering upward vertical velocity, it's crucial to account for the acceleration due to gravity, g. On the surface of the Earth, g is approximately 9.8 meters per second squared, directed downward. When an object is moving upward, g acts to decelerate its vertical velocity until it reaches its highest point and starts descending. Equations of motion. Upward vertical velocity can be described using various equations of motion, depending on the initial conditions and the presence of other forces. One of the fundamental equations governing motion is Vf equals Vi plus At, where Vf is the final velocity, Vi is the initial velocity, A is the acceleration, and T is the time. When considering upward motion, if the object is moving against gravity, the acceleration term A would be negative, indicating deceleration. Projectile motion. Upward vertical velocity is a crucial component of projectile motion. In projectile motion, an object is launched into the air at an angle with a certain initial velocity. The vertical component of this initial velocity contributes to the object's upward vertical velocity. As the object moves upward, its vertical velocity decreases due to the gravitational force until it reaches its highest point and then begins to descend. Maximum height. The maximum height reached by a projectile can be determined using its upward vertical velocity. At the peak of its trajectory, the upward vertical velocity becomes zero before the object starts descending. This maximum height can be calculated using equations of motion and kinematic principles. Energy considerations. Upward vertical velocity also plays a role in energy considerations. As an object moves upward against gravity, it gains potential energy due to its increased height. This potential energy is directly proportional to the object's mass, gravitational acceleration, and height above the reference point. Understanding upward vertical velocity is essential for comprehending a wide range of physical phenomena, from simple freefall motion to complex projectile motion scenarios. Mastery of this concept is crucial for students studying physics and related fields, as it forms the basis for analyzing various types of motion and interactions in the natural world. Question 2. Angular velocity. Understanding motion, angular velocity. Angular velocity is a fundamental concept in physics that describes the rate of change of angular displacement with respect to time. It is commonly denoted by the symbol O omega and is measured in radians per second, rad/s, in the International System of Units, SI. Angular velocity is analogous to linear velocity, which measures the rate of change of linear displacement with respect to time. However, instead of measuring straight-line motion, angular velocity describes rotational motion around an axis. Mathematically, angular velocity over is defined as the ratio of the change in angular displacement delta t to the change in time del t O equals delta del t. Alternatively, in calculus terms, angular velocity can be expressed as the derivative of angular displacement with respect to time, O equals d theta dt, where O equals angular velocity rad by s, delta is change in angular displacement radians, del t equals change in time seconds, d theta or slar dt equals derivative of angular displacement with respect to time. Angular velocity can be either positive or negative depending on the direction of rotation. A positive angular velocity indicates counterclockwise rotation when viewed from above the rotation axis, while a negative angular velocity indicates clockwise rotation. Angular velocity plays a crucial role in understanding rotational motion, such as the rotation of objects like wheels, gears, or celestial bodies. It is also essential in describing phenomena like the Coriolis effect, which influences atmospheric and oceanic circulation patterns. In summary, angular velocity quantifies the rate of change of angular position of an object as it rotates around a fixed axis and is a fundamental concept in physics, particularly in the study of rotational motion. Question 3. Velocity before a shot put hits the ground. Understanding motion. Velocity of a shot put before impact. Velocity before a shot put hits the ground is a critical concept in classical mechanics, often tested on exams such as the MCAT, Medical College Admission Test. In the context of projectile motion, the velocity of the shot put just before it strikes the ground can be analyzed using principles of kinematics and dynamics. When a shot put is thrown into the air, it follows a parabolic trajectory due to the influence of gravity. At any point during its flight, the shot put has both horizontal and vertical components of velocity. The vertical velocity changes continuously due to the acceleration caused by gravity, while the horizontal velocity remains constant, assuming no air resistance. To determine the velocity of the shot put just before it hits the ground, it's crucial to recognize that the vertical velocity component reaches its maximum at the apex of the projectile's trajectory. At this point, the shot put momentarily stops ascending before beginning its descent. However, the horizontal velocity remains unchanged throughout the motion. Mathematically, the velocity of the shot put just before impact can be expressed as the vector sum of its horizontal and vertical velocities. The magnitude of this velocity is the resultant of these components, while the direction is determined by the angle of projection and remains constant unless affected by external factors such as air resistance or wind. Understanding velocity in projectile motion is essential for solving problems involving the range, time of flight, and maximum height of the shot put's trajectory. Mastery of these concepts enables aspiring medical students to apply principles of physics to real-world scenarios, fostering a deeper understanding of biomechanics and sports-related injuries, which are pertinent to medical practice and research.
Question 4. Pendulums and kinetic energy. Energy and dynamics, pendulum mechanics, and kinetic energy. Here's some college-level information about pendulums and kinetic energy that could be relevant for the MCAT. Pendulums. A pendulum is a weight suspended from a pivot so that it can swing freely. The motion of a pendulum can be described by its period, which is the time it takes for the pendulum to complete one full swing. The period of a pendulum is dependent on its length and the acceleration due to gravity. The period of a pendulum, t, can be calculated using the formula t equals 2 pi times L var g, where t is the period of the pendulum, L is the length of the pendulum, and g is the acceleration due to gravity, approximately 9.81 meters squared on the surface of the Earth. This equation demonstrates that the period of a pendulum is independent of the mass of the pendulum bob, but is directly proportional to the square root of the length of the pendulum. Pendulums are used in various applications, including timekeeping devices like pendulum clocks and metronomes, as well as in scientific experiments to measure gravitational acceleration. Kinetic energy. Kinetic energy is the energy an object possesses due to its motion. It is defined as the work needed to accelerate an object from rest to its current velocity. the kinetic energy K of an object with mass m and velocity v can be calculated using the formula K equals 1/2 mv squared e, where K is the kinetic energy, m is the mass of the object, and v is the velocity of the object. This equation shows that kinetic energy is directly proportional to the square of the velocity of the object and directly proportional to the mass of the object. In the context of the MCAT, understanding kinetic energy is crucial for topics related to mechanics, including Newton's laws of motion, work and energy, and concepts in fluid dynamics and thermodynamics. Kinetic energy plays a fundamental role in understanding the behavior of moving objects and is essential for solving various physics problems involving motion and energy transformations. Question 5. Total energy of a moving pendulum. Energy and dynamics. Total energy in motion, pendulum example. Total energy of a moving pendulum. In physics, the total energy of a moving pendulum refers to the sum of its kinetic energy and its potential energy at any given moment. Understanding the total energy of a pendulum is crucial in analyzing its behavior and predicting its motion. 1. Kinetic energy, Ke. Kinetic energy is the energy possessed by an object due to its motion. For a pendulum, the kinetic energy is primarily associated with its swinging motion. The formula for kinetic energy is Ke equals 1/2 mv squared, where m is the mass of the pendulum bob, v is the velocity of the pendulum bob. 2. Potential energy, Pe. Potential energy is the energy possessed by an object due to its position relative to a reference point. In the case of a pendulum, the potential energy is associated with its height above the lowest point in its swing, usually its lowest point of the arc. The potential energy can be calculated using the formula for gravitational potential energy, Pe equals mgh, where m is the mass of the pendulum bob, g is the acceleration due to gravity, approximately 9.81 meters squared on the surface of the Earth, h is the height of the pendulum bob above its lowest point. 3. Total energy, Te. The total energy of the pendulum is the sum of its kinetic energy and potential energy at any point in its motion. Mathematically, it can be expressed as Te equals Pe, Te equal 1/2 m of quadrant plus mgh. It's essential to note that the total energy of a pendulum remains constant, assuming no external forces like friction or air resistance throughout its motion. This conservation of energy principle is a fundamental concept in physics and plays a significant role in analyzing various systems, including pendulums. Understanding the total energy of a moving pendulum not only helps in theoretical analysis, but also finds practical applications in fields such as engineering, mechanics, and even in understanding biological systems like the movement of limbs in animals. In summary, the total energy of a moving pendulum is the combination of its kinetic energy associated with its motion and its potential energy associated with its position relative to a reference point. This total energy remains constant in the absence of external forces, highlighting the principle of conservation of energy. Question 6. Useful work performed in lifting an object from the ground. Energy and dynamics. Work done in lifting objects. Work done in lifting an object. Work, in the context of physics, is defined as the product of the force applied on an object and the displacement of the object in the direction of the force. When lifting an object from the ground, work is performed against the force of gravity. Formula for work. The work done, W, in lifting an object against gravity is given by the formula W equals F d cos θ, where W is the work done, F is the force applied, in this case the force required to lift the object, d is the displacement, the height to which the object is lifted, θ is the angle between the direction of the force and the direction of the displacement. Since lifting an object is typically done vertically, θ is usually 0 and cos and grog equals 1, simplifying the equation. Thus, the formula for work simplifies to W equals Fd, gravitational force. The force exerted by gravity on an object near the surface of the Earth is given by Newton's law of universal gravitation. Fg equals mg, where Fg is the gravitational force, m is the mass of the object, and g is the acceleration due to gravity, approximately 9.8 meters per square, near the surface of the Earth. Calculating work. To calculate the work done in lifting an object from the ground, you need to know the force required to lift the object, which depends on its mass and the acceleration due to gravity and the vertical displacement. Then you can use the formula W equals Fd to find the work done. Example: consider lifting a box with a mass of 10 kilograms from the ground to a height of 2 meters. Using the formula for work, the work done would be W equal to 10 kilo of 9.8 meter to square 2 equal 196 J. So 196 joules of work would be required to lift the box.
Water flow rate refers to the volume of water that passes through a particular point in a given period of time. It is typically measured in units such as liters per second, L's per secs, or cubic meters per hour, m²/s per hour. In fluid dynamics, water flow rate is influenced by several factors, including the properties of the fluid, such as viscosity and density, the characteristics of the conduit through which the water flows, such as diameter and length, and external factors like pressure and temperature. One of the key principles governing water flow rate is Bernoulli's principle, which states that in a fluid flow, an increase in the speed of the fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. This principle helps explain phenomena such as the Venturi effect, where the velocity of fluid increases as it passes through a constriction in a pipe, resulting in a decrease in pressure. The flow rate of water in a pipe can be calculated using the principles of fluid dynamics and conservation of mass. The equation commonly used to calculate flow rate is the volumetric flow rate equation, Q equals A times V, where Q is the volumetric flow rate in cubic meters per second or liters per second. A is the cross-sectional area of the pipe in square meters or square centimeters, and V is the velocity of the water in meters per second. The velocity of water in a pipe can be determined using the equation of continuity, which states that the mass flow rate of fluid in a pipe is constant along its length, assuming the fluid is incompressible. A1 times V1 equals A2 times V2, where A1 and A2 are the cross-sectional areas of the pipe at points 1 and 2 respectively, and V1 and V2 are the velocities of the water at points 1 and 2 respectively. By rearranging this equation, we can solve for velocity at a given point in the pipe, and then use it in the volumetric flow rate equation to determine the flow rate of water. Understanding water flow rate is crucial in various applications, including hydraulic engineering, plumbing systems, and environmental studies. Mastery of this concept is essential for students pursuing fields such as engineering, physics, and environmental science. Spontaneous reactions are fundamental concepts in chemistry, frequently encountered in various contexts, including biochemistry, thermodynamics, and organic chemistry. They are crucial for understanding the behavior of chemical systems and predicting the direction of reactions under different conditions. A spontaneous reaction is a chemical process that occurs without the input of external energy and proceeds in a particular direction under given conditions. These reactions tend to occur naturally, driven by favorable changes in thermodynamic properties. Spontaneous reactions are characterized by a negative change in Gibbs free energy, delta G less than 0. Gibbs free energy is a measure of the energy available to do useful work in a system at constant temperature and pressure. A negative del G indicates that the reaction releases energy and is thermodynamically favorable. Entropy, del S, refers to the measure of disorder or randomness in a system. Enthalpy, del H, is the heat energy exchange during a reaction at constant pressure. Spontaneous reactions often involve an increase in entropy, del S greater than 0, and/or a decrease in enthalpy, delta H less than 0. The spontaneity of a reaction is determined by both enthalpy and entropy changes, as described by the equation delta G equals delta H minus T del S. A negative delta G indicates a spontaneous reaction when delta H is less than 0, exothermic, and/or delta S is greater than 0, increase in disorder. However, even endothermic reactions, del H greater than 0, can be spontaneous if the increase in entropy dominates, T del S greater than delta H. Delta G degree represents the Gibbs free energy change of a reaction under standard conditions, 1 atom in pressure, 298 K temperature, and 1 m concentration. A negative delta G degree indicates a spontaneous reaction under standard conditions. At equilibrium, delta G equals 0, meaning the forward and reverse reactions occur at equal rates. If delta G is less than 0, the reaction proceeds spontaneously in the forward direction towards products. If delta G is greater than 0, the reaction is non-spontaneous under the given conditions and proceeds in the reverse direction. Factors affecting spontaneity include temperature, pressure, and concentration. Increasing temperature can make some endothermic reactions spontaneous by increasing the contribution of entropy. For gaseous reactions, changes in pressure can affect spontaneity, particularly for reactions involving a change in the number of moles of gas. Changes in reactant or product concentrations can shift the equilibrium position, affecting the spontaneity of the reaction. Consider the combustion of methane. CH4 plus 2O2 yields CO2 plus 2H2O. This reaction is highly spontaneous, dLg less than 0, due to the large negative enthalpy change, dH associated with the formation of CO2 and H2O, coupled with a substantial increase in entropy, dS greater than 0, as multiple gaseous molecules are produced from fewer gaseous reactants. Understanding spontaneous reactions is essential for predicting reaction outcomes, designing chemical processes, and interpreting biochemical pathways. Mastery of these concepts is vital for success in the MCAT and for a deeper understanding of chemical systems in general.
Rate constant is a fundamental concept in chemical kinetics, which is the study of the rates at which chemical reactions occur. The rate constant, typically denoted by K, is a proportionality constant that relates the rate of a chemical reaction to the concentrations of the reactants. For a generic reaction, AA plus BB CC plus DD, the rate of the reaction is given by rate equals Ka mB square N, where A and B are the concentrations of reactants A and B respectively, and M and N are the respective reaction orders for A and B. The overall reaction order is the sum of the individual reaction orders, M plus N. The rate constant K depends on several factors, including temperature, the presence of a catalyst, and the specific reaction mechanism. However, it is independent of the concentrations of the reactants. The units of the rate constant depend on the overall reaction order. For a first-order reaction, M plus N equals 1, the units of K are usually expressed in reciprocal seconds, S square minus 1. For second-order reactions, M plus N equals 2, the units are usually expressed in M core 1 S square 1 if the concentrations are in molarity. The value of K can provide important information about the reaction kinetics. A larger value of K indicates a faster reaction rate, while a smaller value of K indicates a slower reaction rate. Experimental determination of the rate constant often involves measuring the initial rates of reaction at different initial concentrations of the reactants, and then using the rate equation to determine K. Overall, understanding the rate constant is crucial for predicting and analyzing the kinetics of chemical reactions, which has implications in fields ranging from environmental science to pharmaceuticals. Increased pressure on the system and reaction quotient are fundamental concepts in chemical equilibrium, which is a critical topic in general chemistry and biochemistry, often tested on the MCAT, Medical College Admission Test. Let's delve into each concept. When the pressure of a system at equilibrium is increased, the system responds by favoring the reaction that produces fewer moles of gas. This is based on Le Chatelier's principle, which states that a system at equilibrium will respond to any stress applied to it in such a way as to minimize the effect of the stress. Impact on gaseous equilibrium. 1. Decrease in volume. Increasing pressure can occur by decreasing the volume of the container. In a system with gaseous reactants and products, decreasing the volume increases the pressure. The system will shift to favor the side with fewer moles of gas to counteract the increase in pressure. 2. Increase in volume. Conversely, if the volume is increased, the pressure decreases. In this case, the system will shift to the side with more moles of gas to compensate for the decrease in pressure. Reaction quotient Q is a mathematical expression used to determine whether a system at any given point in time is at equilibrium or not. It's similar to the equilibrium constant K, but calculated using concentrations or partial pressures of reactants and products at a particular moment during the reaction, rather than at equilibrium. Calculation 1. For gaseous equilibria, the reaction quotient Q for gaseous equilibria is calculated using partial pressures of reactants and products, denoted as P reactants and P products respectively. Q equals P products, P reactants. 2. For aqueous equilibria, if the reaction involves species in solution, concentrations are used instead of partial pressures. Q equals products, reactants. Interpretation. 1. If Q is less than K, the system has more reactants than products, indicating the reaction has not yet reached equilibrium. The system will shift towards the products to reach equilibrium. 2. Q equals K. When Q equals K, the system is at equilibrium. 3. QK. If Q is greater than K, the system has more products than reactants, suggesting the reaction has already passed equilibrium. The system will shift towards the reactants to establish equilibrium. Understanding these concepts is essential for predicting how changes in pressure and concentration affect a system at equilibrium, which is crucial for solving equilibrium-related problems on the MCAT. A rock is thrown vertically upward from the edge of a cliff with an initial velocity of 20 meters per second. Which of the following statements about the upward vertical velocity of the rock is true? A. The upward vertical velocity of the rock decreases as it rises. B. The upward vertical velocity of the rock remains constant throughout its motion. C. The upward vertical velocity of the rock increases as it rises. D. The upward vertical velocity of the rock is 0 at the highest point of its trajectory. A race car is moving along a circular track with a radius of 100 meters. If the race car completes one full lap in 40 seconds, what is the angular velocity of the race car in radians per second? A. Pi 4 rad bar s. B. 2 rad rad. C. Pi rad bar s. D. 2 pi rad bar s.
Question 3. Velocity before a shot put hits the ground. A shot put is thrown with an initial velocity of 15 meters per second at an angle of 45 degrees above the horizontal. Neglecting air resistance, what is the velocity of the shot put right before it hits the ground? A. 15 meters per C, 10.6 meters per D, 21.2 meters per S. Question 4. Pendulums and kinetic energy. Which of the following scenarios best illustrates the relationship between a pendulum's length and its kinetic energy? A. A pendulum with a longer length swings with greater kinetic energy than a pendulum with a shorter length. B. A pendulum with a shorter length swings with greater kinetic energy than a pendulum with a longer length. C. The kinetic energy of a pendulum is independent of its length. D. The kinetic energy of a pendulum is directly proportional to its length. Question 5. Total energy of a moving pendulum. A pendulum of mass m meter and length ll is swinging back and forth with an amplitude aa. At the lowest point of its swing, the total energy of the pendulum is composed of which of the following? A. Potential energy only. B. Kinetic energy only. C. Both potential and kinetic energy. D. Neither potential nor kinetic energy. Question 6. Useful work performed in lifting an object from the ground. A student performs an experiment to determine the useful work required to lift an object from the ground to a height of 2 meters. The object has a mass of 5 kilograms and the student exerts a constant force of 50 newtons upwards. If the object is lifted at a constant velocity, what is the useful work performed by the student? A. 0 joules. B. 100 joules. C. 150 joules. D. 200 joules. Question 7. Water flow rate. Which of the following factors would not affect the rate of water flow through a pipe? A. Diameter of the pipe. B. Length of the pipe. C. Temperature of the water. D. Density of the water. Question 8. Spontaneous reaction. Which of the following statements accurately describes a spontaneous reaction? A. A spontaneous reaction always proceeds rapidly. B. A spontaneous reaction always leads to an increase in entropy. C. A spontaneous reaction always requires an input of energy. D. A spontaneous reaction always occurs without the need for an external influence. Question 9. Rate constant. Which of the following statements accurately describes the relationship between temperature and the rate constant K in a chemical reaction? A. As temperature increases, the rate constant decreases. B. The rate constant is independent of temperature. C. The rate constant increases exponentially with temperature. D. Temperature has no effect on the rate constant. Question 10. Increased pressure on the system and reaction quotient. Consider the following reaction at equilibrium. A of G plus BG plus DG. If the pressure on the system is increased by reducing the volume of the container, which of the following correctly describes the changes to the reaction quotient QQ and the direction in which the reaction will proceed to reestablish equilibrium? A. QQ increases, the reaction shifts to the right. B. QQ decreases, the reaction shifts to the left. C. Q increases, the reaction shifts to the left. D. QQ decreases, the reaction shifts to the right. Question 1. Upward vertical velocity. A projectile is launched vertically upward from the ground with an initial velocity of 20 meters per second. What is its upward vertical velocity at its highest point? A. 20 meters per second. B. 0 meters per second. C. Minus 20 meters. D. It cannot be determined. Correct answer. B. 0 meters per second. Explanation. At the highest point of its trajectory, the vertical velocity of the projectile momentarily becomes 0. This occurs because at the peak of its flight, the projectile momentarily stops moving upward before it begins to fall back down due to gravity. Therefore, at the highest point, the upward vertical velocity is 0 meters per second. 20 meters per second. This is incorrect because 20 meters per second represents the initial velocity of the projectile, not its velocity at the highest point. C. Minus 20 meters per second. This is incorrect because the negative sign indicates a downward velocity. At the highest point, the velocity is not downward. Rather, it is momentarily 0. D. It cannot be determined. This is incorrect because the velocity at the highest point can indeed be determined based on the principles of projectile motion. The velocity is momentarily 0 at the peak of its trajectory. Question 2. Angular velocity. A race car is moving along a circular track with a radius of 100 meters. If the race car completes one full lap in 40 seconds, what is the angular velocity of the race car in radians per second? A. Pi 4 res. B. Pi 2 rad res. C. Pi rad says. D. 2 pi rad perfect. Correct answer. D. 2 pi rad as explanation. Angular velocity is defined as the rate of change of angular displacement with respect to time. In this case, the race car completes one full lap around the circular track, which corresponds to an angular displacement of 2 pi radians. The time taken to complete one lap is 40 seconds. Therefore, the angular velocity is 2 pi radians divided by 40 seconds, which equals pi for 20 rad s. However, we are asked for the angular velocity in radians per second, so the correct answer is 2 pi res, which is option D. Let's analyze the other options. A. Pi 4 rad secs. This option is incorrect because it represents only a quarter of the correct angular velocity. It seems to be derived from 2 pi 8, which might be a common mistake in calculations. B. Pi 2 rad s. This option is incorrect because it represents half of the correct angular velocity. It seems to be derived from 2 pi 4, which might be another common mistake in calculations. C. Pi rad bert s. This option is incorrect because it represents only half of the correct angular velocity. It seems to be derived from 2 pi over 2, which again is a miscalculation. So the correct answer is D, 2 pi rad first s, as it reflects the correct angular velocity for the race car moving along the circular track. Question 3. Velocity before a shot put hits the ground. A shot put is thrown with an initial velocity of 15 meters seconds at an angle of 45 degrees above the horizontal. Neglecting air resistance, what is the velocity of the shot put right before it hits the ground? A. 15 meters per second. B. 0 meters per second. C. 10.6 per second. D. 21.2 meters. Correct answers 10.6 meters per second. Explanation. To solve this problem, we can break down the initial velocity of the shot put into its horizontal and vertical components using trigonometry. Since the angle of launch is 45 degrees, the horizontal and vertical components are equal. The horizontal component is 15 meters per second times the cosine of 45 degrees, which is approximately 10.6 meters per second. The vertical component is 15 meters per second times the sine of 45 degrees, which is also approximately 10.6 meters per second. At the highest point of the trajectory, the vertical component of the velocity is 0 meters per second as the shot put momentarily stops moving upward before falling downward. However, the horizontal component remains unchanged. Therefore, right before the shot put hits the ground, its velocity will be equal to its horizontal component, which is approximately 10.6 meters per second. Thus, option C is correct. Option A, 15 meters per second. This represents the initial velocity of the shot put, but it doesn't account for the effect of gravity pulling it downward. Option B, meters per second. This represents the vertical velocity at the peak of the trajectory when the shot put momentarily stops moving upward. However, it fails to consider the horizontal motion. Option D, 21.2 meters per second. This appears to double the initial velocity, likely a calculation error. It doesn't consider the change in velocity due to the influence of gravity. Question 4. Pendulums and kinetic energy. Which of the following scenarios best illustrates the relationship between a pendulum's length and its kinetic energy? A. A pendulum with a longer length swings with greater kinetic energy than a pendulum with a shorter length. B. A pendulum with a shorter length swings with greater kinetic energy than a pendulum with a longer length. C. The kinetic energy of a pendulum is independent of its length. D. The kinetic energy of a pendulum is directly proportional to its length. Correct answer. A. A pendulum with a longer length swings with greater kinetic energy than a pendulum with a shorter length. Explanation. A pendulum's kinetic energy is directly related to its potential energy, which in turn depends on its height from the lowest point of its swing. When a pendulum swings, it converts its potential energy to kinetic energy and vice versa. The potential energy of a pendulum is determined by its height, which is directly related to its length. Therefore, a pendulum with a longer length will swing to a greater height and thus possess greater potential energy. Consequently, it will also have greater kinetic energy as it swings down from this greater height. This relationship is described by the equation for the potential energy of a pendulum, PE equals mgh, where m is mass, g is acceleration due to gravity, and h is the height. Option B is incorrect because a shorter pendulum swings to a lesser height and thus has less potential energy and subsequently less kinetic energy. Option C is incorrect because the kinetic energy of a pendulum is indeed influenced by its length. Option D is incorrect because the kinetic energy of a pendulum is not directly proportional to its length, but rather to its potential energy, which is related to its length and height. Question 5. Total energy of a moving pendulum. A pendulum of mass m and length L is swinging back and forth with an amplitude A. At the lowest point of its swing, the total energy of the pendulum is composed of which of the following? A. Potential energy only. B. Kinetic energy only. C. Both potential and kinetic energy. D. Neither potential nor kinetic energy. Answer. C. Both potential and kinetic energy. Explanation. At the lowest point of its swing, the pendulum has its maximum kinetic energy and minimum potential energy. According to the law of conservation of energy, the total mechanical energy of the system, the pendulum, remains constant. At the lowest point of its swing, all of the pendulum's potential energy has been converted into kinetic energy. This is because the gravitational potential energy is at its minimum when the pendulum is at its lowest point. As the pendulum swings upward, it loses kinetic energy and gains potential energy until it reaches its highest point, where it has maximum potential energy and zero kinetic energy. Therefore, at the lowest point of its swing, the total energy of the pendulum is a combination of both potential and kinetic energy. Option A, potential energy only, is incorrect because at the lowest point of its swing, the pendulum has maximum kinetic energy and minimum potential energy. Option B, kinetic energy only, is incorrect because at the lowest point of its swing, the pendulum has both kinetic and potential energy, not just kinetic energy. Option D, neither potential nor kinetic energy, is incorrect because at the lowest point of its swing, the pendulum possesses kinetic energy due to its motion and gravitational potential energy due to its position. Question 6. Useful work performed in lifting an object from the ground. A student performs an experiment to determine the useful work required to lift an object from the ground to a height of 2 meters. The object has a mass of 5 kilograms, and the student exerts a constant force of 50 newtons upwards. If the object is lifted at a constant velocity, what is the useful work performed by the student? A. 0 joules. B. 100 joules. C. 150 joules. D. 200 joules. Correct answer, C. 150 joules. Explanation. To determine the useful work performed in lifting the object, we must consider the force exerted and the distance over which it acts. The formula for work done W is given by W equals F times D times cos theta, where F is force applied in newtons, D is distance moved in the direction of the force in meters, theta is angle between the force vector and the direction of displacement, in this case 0 degrees as the force is acting vertically upwards. Given F equals 50N upwards, D equals 2M. Substituting these values into the formula, W equals 50N times 2M times cos 0 degrees. W equals 50N times 2M times 1. W equals 100J times 1. W equals 100J. However, the question specifies useful work and the object is being lifted at a constant velocity. When an object is moved at a constant velocity, the net work done on it is zero. This means that the work done by the lifting force is equal and opposite to the work done by gravity. The work done against gravity is equal to the gravitational potential energy gained by the object, which is given by W gravity equals m times g times h, where m is mass of the object in kilograms, g is acceleration due to gravity, approximately 9.8 meters per second squared, h is height to which the object is lifted in meters. Given m equals 5 kilograms, g equals 9.8 meters per second squared, h equals 2 mem. Substituting these values into the formula, W gravity equals 5 kilograms times 9.8 meters per second squared times 2 mem. W gravity equals 98 j kilograms times 2 mem. W gravity equals 196 j. Since the net work done on the object is zero, the useful work performed by the student is equal and opposite to the work done against gravity. W useful equals minus W gravity. W useful equals minus 196 j. Thus, the correct answer is 150 joules, option C, as this represents the useful work performed by the student in lifting the object. Option A, 0 joules, is incorrect because there is work being done against gravity. Option B, 100 joules, is incorrect because it represents the work done by the lifting force but doesn't account for the work done against gravity. Option D, 200 joules, is incorrect because it overestimates the work done, considering only the lifting force and not accounting for the work done against gravity.
Question 7. Water flow rate. Which of the following factors would not affect the rate of water flow through a pipe? A. Diameter of the pipe. B. Length of the pipe. C. Temperature of the water. D. Density of the water. Correct answer, D. Density of the water. Explanation. Diameter of the pipe. The rate of water flow through a pipe is directly proportional to the fourth power of the pipe's radius, or diameter. This relationship is described by Poiseuille's law. Therefore, increasing the diameter of the pipe would increase the flow rate, making option A correct. B. Length of the pipe. The longer the pipe, the greater the resistance to flow due to friction between the water and the pipe walls. This resistance reduces the flow rate. Thus, the length of the pipe does affect the rate of water flow, making option B incorrect. C. Temperature of the water. The viscosity of water decreases as temperature increases. Lower viscosity reduces resistance to flow, thereby increasing the flow rate. Therefore, the temperature of the water does affect the rate of water flow, making option C incorrect. D. Density of the water. The density of the fluid does not directly affect the rate of flow through a pipe. While density can influence other aspects of fluid dynamics, such as buoyancy, it does not directly impact the rate of flow through a pipe, as long as the fluid remains incompressible. Therefore, option D is the correct answer. In summary, options A, B, and C are incorrect because they all affect the rate of water flow through a pipe, whereas option D is correct because the density of the water does not directly impact the flow rate. Question 8. Spontaneous reaction. Which of the following statements accurately describes a spontaneous reaction? A. A spontaneous reaction always proceeds rapidly. B. A spontaneous reaction always leads to an increase in entropy. C. A spontaneous reaction always requires an input of energy. D. A spontaneous reaction always occurs without the need for an external influence. Correct answer. B. A spontaneous reaction always leads to an increase in entropy. Explanation. A. This statement is incorrect. Spontaneous reactions can proceed at varying rates. Some may occur rapidly, while others may occur slowly. B. This statement is correct. According to the second law of thermodynamics, a spontaneous reaction is one that leads to an increase in entropy, disorder, of the system and its surroundings. This increase in entropy is a fundamental characteristic of spontaneous processes. C. This statement is incorrect. Spontaneous reactions can either release or absorb energy. The key factor in determining spontaneity is the change in Gibbs free energy, delta G, not the requirement for energy input. Spontaneous reactions have a negative delta G, indicating that they release energy, but this does not necessarily mean they require an input of energy. D. This statement is incorrect. Spontaneous reactions occur based on the thermodynamic favorability of the reaction, not necessarily without the need for external influence. While spontaneous reactions can occur without continuous external intervention once initiated, they may still require initial activation energy to overcome energy barriers. In summary, option B is the correct answer because it accurately describes the thermodynamic aspect of spontaneous reactions, which is the increase in entropy. Options A, C, and D are incorrect due to their inaccuracies regarding the speed of reaction, energy requirement, and need for external influence, respectively. Question 9. Rate constant. Which of the following statements accurately describes the relationship between temperature and the rate constant K in a chemical reaction? A. As temperature increases, the rate constant decreases. B. The rate constant is independent of temperature. C. The rate constant increases exponentially with temperature. D. Temperature has no effect on the rate constant. Correct answer C. The rate constant increases exponentially with temperature. Explanation: A. Incorrect. According to the Arrhenius equation, an increase in temperature generally results in an increase in the rate constant rather than a decrease. B. Incorrect. The rate constant is indeed dependent on temperature, as elucidated by the Arrhenius equation. C. Correct. The Arrhenius equation, which relates the rate constant to temperature, states that K equals A EEEA RT, where A is the pre-exponential factor, EA is the activation energy, R is the gas constant, and T is the absolute temperature. This equation demonstrates that the rate constant increases exponentially with temperature. D. Incorrect. Temperature profoundly influences the rate constant, as indicated by the Arrhenius equation. An increase in temperature generally leads to a higher rate constant, while a decrease in temperature results in a lower rate constant. Question 10. Increased pressure on the system and reaction quotient. Consider the following reaction at equilibrium: Ag plus Bg, Cg plus Dg. If the pressure on the system is increased by reducing the volume of the container, which of the following correctly describes the changes to the reaction quotient QQ and the direction in which the reaction will proceed to reestablish equilibrium? A. QQ increases, the reaction shifts to the right. B. QQ decreases, the reaction shifts to the left. C. QQ increases, the reaction shifts to the left. DQ decreases, the reaction shifts to the right. Answer: B. QQ decreases, the reaction shifts to the left. Explanation: when the pressure on a system at equilibrium is increased by reducing the volume, the system will respond by shifting the equilibrium position to counteract this change and relieve the stress. According to Le Chatelier's principle, if the volume decreases, thus increasing the pressure, the equilibrium will shift in the direction that reduces the total number of moles of gas. In this reaction, since there are 4 moles of gas on the left side, A and B, and only 2 moles of gas on the right side, C and D, decreasing the volume will increase the pressure. To counteract this increase in pressure, the system will shift to the side with fewer moles of gas, which is to the left. As a result, the reaction quotient QQ will decrease. The reaction quotient QQ is the ratio of the concentrations of the products to the concentrations of the reactants at any point in time during the reaction. If QQ is less than the equilibrium constant KK, the reaction will proceed in the forward direction to reach equilibrium. Therefore, if QQ decreases, the reaction will shift to the left to consume some of the excess products and produce more reactants until equilibrium is reestablished. Options A, C, and D are incorrect because they incorrectly describe the changes to QQ and the direction in which the reaction shifts. Yo, it's the med student life, but it's a heavy load in this world of medicine where dreams are stowed. Books stacked high like weights on my back. In this marathon of learning, gotta keep on track. Lectures and labs, they never seem to end. In this hustle for success, gotta transcend. But I'll push through the grind, find my stride. In this medical journey, I won't hide. Anatomy dissections, like a workout session. In this quest for knowledge, gotta make an impression. Pushing through fatigue, like a warrior bold. In this world of medicine, I'll break the mold. In the hustle and the grind, but I'm lifting weights. Heavy workload, but I won't deflate. In this world of medicine, where greatness awaits, I'm just a med student breaking the gates. Late nights in the library, burning the midnight oil. In this quest for excellence, gotta toil. Practice exams and quizzes like reps in the gym. In this pursuit of mastery, I'll never skim. But I'll find balance in the chaos, stay composed. In this medical journey, where success is imposed. No longer overwhelmed by the weight of it all, in this world of medicine, I'll stand tall. Staying fit physically, mentally sharp, in this journey of growth, I'll leave my mark. No longer held back by the workload's might, in this medical world, I'll shine bright. In the hustle and the grind, but I'm lifting weights. Heavy workload, but I won't deflate. In this world of medicine where greatness awaits, I'm just a med student, breaking the gates. So I'll embrace the challenge, with all my might. In this quest for knowledge, I'll take flight. No longer daunted by the heavy load, in this medical journey, I'll hit the road. Yo, it's the med student grind, but I'll make it through. In this journey of medicine, I'll stay true. No longer weighed down by the workload's sway, in the world of medicine, I'll find my way.
A few meditations from the Word of God. Ecclesiastes 9:18. Wisdom is better than weapons of war, but one sinner destroyeth much good. Exodus 23:22-23 NIV. If you listen carefully to what he says and do all that I say, I will be an enemy to your enemies and will oppose those who oppose you. 23. My angel will go ahead of you and bring you into the land of the Amorites, Hittites, Perizzites, Canaanites, Hivites, and Jebusites, and I will wipe them out. Joshua 1:5 KJV. There shall not any man be able to stand before thee all the days of thy life. As I was with Moses, so I will be with thee. I will not fail thee, nor forsake thee. Survival question alert. What stresses you out the most about living in the United States? Please comment below. What concept or topic intrigued you the most from the video? Please comment down below. How do you relate these physics principles to real-world scenarios? Please comment down below. Thank you for joining us on this exploration of physics. We hope you've gained insights into these fascinating topics. Subscribe for more educational content and stay curious. Hello there, I am Angelique Granville, and I'm a professional listener, digital products entrepreneur, and content creator. I have a degree in biology from Adelphi University, and I am passionate about helping allied health professionals succeed. I am here to help you get into medical school. On this channel, I share my tips and hacks on how you can pass your entrance exams so you can get into medical school. Do you want to talk to me for an hour about your life and your problems? Check out my therapy programs. The link is in the description. It says, "Let me help you in life." If you are getting value from this content, I urge you to like, subscribe, and share this video with all of the pre-medical students, biology students and majors, physics majors and engineering majors that you know. If you know anyone who is struggling to study for the MCAT, please tell them about the Hospital Near Me Medical Career Training Channel. Together, we can conquer you, getting into medical school, and feel better about being accepted by the college of my choice. Please hit the notification bell so that you never ever miss another one of my videos. If you haven't already liked this video, make sure to give it a big thumbs up and send this video to at least 3 people. I know you can think of them. If somebody pops in your head right now and send it to them, WhatsApp, Facebook, TikTok, LinkedIn, and Instagram, challenge them to do it with you, and you can get results together. Come and take my easy MCAT exam. If you are getting value from this channel, all I ask is that you let my ads play on the video, and if you could bless my PayPal, Monzo, Cash App, Venmo, Buy Me a Coffee, GoFundMe, Patreon, or give me a thank you donation of $1 to $5, or with a donation of any amount, it would be greatly appreciated. I am saving up for a new home as my old one got severely damaged in Hurricane Sandy and left me homeless. I want to thank you for watching the Hospital Near Me Medical Career Channel for allied health professionals. I look forward to being a part of your medical school journey and being a part of your own growth. Walk with God. Thanks a bunch. Thank you for watching, and stay tuned for the Shopping Network.